Welcome everyone to our virtual chat for the celebration of women and girls in astronomy. Hello everyone, I am Dr. Sheila Kanani, Education, Outreach and Diversity Officer. Welcome. Sorry about that everybody, just a sudden feedback, hopefully that won't come back. So starting again, I just wanted to say welcome. So I'm the Education, Outreach and Diversity Officer at the Royal Astronomical Society. And the Society encourages the study of astronomy, geophysics and space science. This year, the RAS is delighted to take part in the IAU's celebration of women and girls in astronomy with this live stream of 30-minute chats highlighting some of our amazing RAS fellows, particularly the women. So just to let you know, we've had numerous talks by women and on women astronomers over the years. A couple to note are the Women of the RAS by Dr. Mandy Bailey and Women in the Stars by Dr. Helen Cluse. We also have had various live streaming events, including the Weird and Wonderful World of Uranus with the University of Leicester's PhD student, Emma Thomas, who allowed us to learn more about what astronomers really do. While observing her collecting data about the aurora of Uranus from the infrared telescope facility atop Mauna Kea in Hawaii. All of these sorts of things can be found at the Royal Astronomical Society's YouTube channel. And if you haven't seen it yet, the RAS released its bicentenary timeline. We made sure it highlighted many of the women astronomers who contributed to astronomy over the last 200 years. It's available via our website and on Instagram. We hope you'll check them out after our chat with our current guest. So I'm delighted to say that we have with us today Dr. Jo Barstow, who's currently a research fellow at the Open University. She grew up in Leicestershire and her first experience of scientific research was as a 16-year-old summer student working with one of the teams behind Beagle 2, the Beagle 2 Mars lander. And this has inspired her ongoing fascination with planets. I'll let her tell you more, but first, just a quick note that we will have a Q&A at the end, so please do post questions via Zoom or YouTube, depending on where you're watching us. Thank you everyone for being here, and thank you to Dr. Barstow for being with us particularly. I'm looking forward to hearing more about your story.
Thank you very much for the introduction, Sheila. I will just share my slides and we will get going. Great, so my science story is called A Tale of Two Telescopes, and I'm going to talk about what we hope to be able to achieve over the next few years, studying exoplanets with the James Webb Space Telescope and the Ariel spacecraft. If you do want to ask me questions about this later on, you can do so via Twitter, and I've put my Twitter handle there on the first page of the talk. But first, why do we actually bother studying exoplanets? Well, they can really help us answer some fundamental questions. They are part of the story of how we got here, how the Earth formed. We might be able to find other habitable or maybe even inhabited planets elsewhere in the galaxy. And from a purely sort of physics perspective, learning about other planets tells us more about how our own planet and the other planets in our solar system work. Normally, if we want to learn about something as a scientist, you would often go into the laboratory and do an experiment. Now, we can't do an experiment on the scale of a whole planet, but what we can do is look at all of the other examples that are out there. And those are what we need to use to tell us what's going on. Until 1995, this was all we had to go on, the solar system. These are the planets that orbit our sun. And they consist of 4 small rocky planets that are close to the sun. And we call these the terrestrial planets, which just means similar to the Earth, Earth-like. And 4 large planets that are mostly just big balls of gas further from the sun. And these larger planets are made mostly of hydrogen and helium, which are the 2 most common chemicals that are present in the universe. And we really didn't think that we would see anything much different to this if we ever found planets around other stars. So imagine the shock when the first planet discovered orbiting another star like the sun. This planet, 51 Pegasi b, this is an artist's impression in case you were wondering, was actually a Jupiter-sized planet, but instead of being quite a long way away from the sun, taking several years to go around its star, it actually orbits its star in just 4 days. So we very quickly found out that what we understood about planets just from the solar system really was far from being representative of what's actually going on. How do we actually discover exoplanets? Well, as you can imagine, it's not necessarily the easiest thing to do. Some of you might have been lucky enough to see a planet yourself. If you look up on a nice clear night without too much moon, and it's the right time of year for a particular planet, then you can see Jupiter, you can see Venus, and you can see Mars, all without the need for binoculars or telescopes, just with the naked eye. But you can't see any of those objects during the day. And that's because during the day, the sun is in the sky, and the sun is big and bright and hot by comparison with the other planets in the solar system. And we have exactly this problem when we're trying to look for planets around other stars. You're looking for something that's a very, very, very long way away next to something that is much bigger and hotter and brighter. It's like looking for a glowworm next to a lighthouse. So how do we go about detecting a planet? Well, one of the methods that we've used to find exoplanets, and at the moment this is the most successful, is something called the transit method. So it relies on a little bit of luck. If an exoplanet and its star are lined up just right from our point of view, then as the planet orbits, at some point in its orbit, it will cross in front of the star from our perspective, and it will block some of the starlight. If we are monitoring that star and measuring the amount of light coming from the star, then we'll see a dip in how much light we're receiving because the planet blocks some of it. If we see that dip happen again and again and again regularly, then we've detected a planet orbiting the star. And the amount of light that's blocked depends on the size of the planet. So if you had a Jupiter-sized planet around a sun-like star, you'd lose about 1% of the starlight. If, on the other hand, you had a rocky planet like the Earth, it would be about 1 part in 10,000. But how on earth do we actually find out any detail about these planets if we can't even see them directly? Well, this is where we use a technique called spectroscopy. And this is all about looking for fingerprints of particular chemicals. This is a sketch of a spectrum of our sun. If we were to split up the light coming from our sun into all of its different colours, then some of those colours would be effectively missing. We'd see some dark lines on this rainbow that we call a spectrum. And I've labelled them here with different chemical species. So the ones labelled Ca, that's calcium, H is hydrogen, Fe is iron, Na is sodium, and O2 is oxygen, 2 oxygen atoms stuck together. We use this technique to learn what chemical species are present in the outer layers of stars, but also we can use it for the atmospheres of planets. And in fact, this is how we know what stars are made of. This is the way that we have learned this, by looking for these missing regions of the spectrum, these missing colours of light. Now, the way that this works is that stars are hot things, and the light coming from the center of the star passes through the cooler layers on the outside of the star. And when the gas in those cooler layers absorbs some of that light, then you see these characteristic fingerprints. That works in exactly the same way, of course, if you've got a planet passing in front of the star. Now, there'll be some of the planet that's completely opaque to all colors of light, but the atmosphere, the shell of gas that surrounds the solid bit of the planet, or the opaque bit, that's going to be transparent to some colors, but not to others. So to take as an example, sodium. So if I flick back to this side, you see that there are two bands that are attributed to sodium here, and they are kind of an orangey yellow color. Those of you that are old enough may remember that street lamps used to be that kind of orangey yellow color, and that was because the light in street lamps was made by heating up some sodium gas and making it very, very hot and excited. So if a planet happens to have sodium gas in its atmosphere, Then light that's a bit yellower than the colour absorbed by sodium will make it through the atmosphere, and light that's a bit oranger will make it through the atmosphere. But that very specific orange-yellow colour is going to get blocked. The sodium gas in the planet's atmosphere will eat away at that light. And what that means is if we watch the planet transit, but this time, instead of just looking at all the light together, we split the light up into its different colours, the planet actually looks bigger in that colour where sodium is absorbing. We see what we call a deeper transit. More of the starlight is blocked. And this is an example of that happening for real. This is an observation from the Very Large Telescope. That's a ground-based telescope in Chile. And when we've on the bottom here, we've got something called wavelength. Effectively, that's colour going from blue on the left-hand side to red on the right-hand side. And roughly in the middle of that, you can see that there's a big spike. And what we're measuring on the y-axis, the up and down axis, is how big the planet appears, how much of that starlight is being blocked. And that big spike is sodium gas. It's sodium gas in the planet's atmosphere absorbing some of the starlight. And you can see in this diagram that we've got some dashed lines marked that correspond to some other smaller spikes. That's lithium and also potassium. What you're looking at in this picture, the black points with these sort of whiskers that are the error bars, that's the actual observation, and the red line is a model that's been fitted to that observation. So you can see it matches up pretty well with what we were predicting. Now, detecting sodium, that's great, but what we're actually interested in to a large extent with looking at planetary atmospheres is not things like sodium and potassium, which are atomic species. We're interested in things like water vapor and carbon dioxide. Those are molecules. And instead of absorbing visible colours of light, molecules tend to absorb in the infrared. And their fingerprints tend to be a little bit messier. So rather than just having some nice, neat lines, we have bands of multiple different lines, and they tend to overlap. So we can't usually just look at a spectrum and say that we've detected a molecule. We have to be a little bit cleverer. So what I actually spend most of my work time doing, at least when I'm doing research, is making models of planet atmospheres with different amounts of different gases in and simulating what happens when light passes through that atmosphere, and then trying to match those simulations up with an observation. So in this diagram, the white line is an observation. So going from left to right, we're going from shorter to longer wavelength in the infrared, and then up and down, like in the previous chart I showed you, is how big the planet seems to be, how much starlight is blocked. And we're trying to match that wiggly line with a simulation. And in this case, I think you can see that the atmosphere that had the right ingredients to match the observation was the green atmosphere, because the wiggly line produced by the green model matches up quite well with the white line. And this is an example again of doing that in reality. So this is an observation of a different planet. This one's called WASP 121b. And this is a bit like 51 Pegasi b, that first exoplanet to be discovered. It's a Jupiter-sized planet that orbits really, really close to its parent star. But this one is around a quite bright star, and it's even closer than 51 Pegasi b. So it's what we call an ultra-hot Jupiter. This planet is actually the same temperature as some cool stars. It's over 2,500 Kelvin. That's about 2,000 degrees centigrade. That's very, very hot. So it has some really weird stuff in its atmosphere. Now, in the same way as the previous chart I showed you, that the points with the whiskers on, that's the actual observations from the telescope. In this case, it's the Hubble Space Telescope. And the lines underneath, the different coloured lines, are different models that we've tried to match. And just to make it a bit easier to see, I'm labelling some of the chemicals that we think we found in this spectrum. Over on the left, we've got something called SH, that's sulfur and hydrogen together. That's a chemical species that actually doesn't hang around for very long normally, so we call it a radical. It reacts quite fast. Then the thing that produces a lot of really wiggly lines in the middle, that's VO, vanadium oxide. That's a metal oxide. On Earth, that would be solid, that would be in rocks, but this planet is so hot, it's actually a gas. The same for this thing FeH, that's iron hydride. And then funnily enough, over on the far right-hand side, we've got H2O, plain old water vapor. And surprisingly enough, water vapor crops up in a huge number of these planets. It's actually around in most of them. So we're already able to do this with things like the Very Large Telescope and Hubble, but this is going to get a lot more exciting over the next 10 years or so, because we're getting two awesome new space telescopes that are both going to be great for exoplanet spectroscopy. And those are the James Webb Space Telescope and Ariel. And they're a little bit different. So they're going to give us some different types of information. So James Webb, you may have seen it launched on Christmas Day, very, very successfully, and it's spent the weeks since then opening itself out, deploying its sunshade, deploying its mirror. So the mirror, as you can see in the picture, it's segmented, and some of that was actually folded in on itself during launch. The reason for that is it's a very big mirror. It's 25 square meters. Hubble's mirror is a little bit over 1 square meter, so you can see how much bigger it is. And it has 4 different instruments that cover a range from the red end of the visible spectrum through to about the middle of what we call the infrared. So it's going to be perfect for looking for molecules like water vapor and carbon dioxide in exoplanet atmospheres. It's also capable of quite high spectral resolution. And by spectral resolution, we mean that we can split the colors of light up quite finely and look at them individually. Ariel, on the other hand, it's quite a bit smaller because it's a much smaller mission. It's not a big multinational mission with NASA and ESA. It's just a European Space Agency mission, so just has participation from Europe. It's actually led from the UK. And it has about 0.6 square meters of mirror. So it's not going to collect as much light as James Webb, but it covers about the same part of the spectrum, from the red visible about to the middle of the infrared. It doesn't have quite such good resolution, so it's not going to be able to split the colors up quite as finely. But the key difference between the two actually is that James Webb is a multi-purpose telescope. So James Webb is going to be looking at absolutely everything you could think of in astronomy. So cosmologists will use James Webb, people who study galaxies, astrochemists who look at the gas in between stars. We're all going to be using James Webb. And that means we're going to be competing for time. Ariel, on the other hand, is a dedicated mission that's just designed to look at exoplanets that transit. That's all it's going to do. So it's launching in about 7 years' time, hopefully, and they'll hopefully be operational together. So what can we do with each of these things? Well, with James Webb, because it's got such a big mirror and it's going to collect such a lot of light, then we can start to be able to do a good job even for quite small planets, potentially planets that are like the planets in our own solar system, Earth and Venus. And one of the ways we might be able to look for a planet that's like Earth is to look for a gas called ozone. Now, ozone is 3 oxygen atoms stuck together. And you're not likely to get a lot of ozone unless you have a planet with a lot of oxygen in its atmosphere. Now, the reason we've got a lot of oxygen in our atmosphere is because of life, because plants and bacteria make oxygen and put it into the atmosphere. And ozone is made when ultraviolet light from a star reacts chemically with oxygen and pulls it apart and sticks it together in a different way. So you get 3 oxygen atoms stuck together. Now, with James Webb, we could see ozone in an exoplanet's atmosphere. So this is a pretend observation with James Webb. It's a simulated observation that I made, compared with some different models for an Earth-sized planet with an Earth-like atmosphere. And where I've highlighted there, that bump in that sort of very wiggly up and down spectrum, that bump is ozone. And if you saw a bump there, it couldn't really be explained with anything else. So you would know that you detected ozone in another planet's atmosphere. So we know that we have the capability to do this. And not only that, we actually know of some planets that we could try this out on. So orbiting a fairly small red star that's quite close by to us is something called the TRAPPIST-1 system. It's a group of 7 rocky planets, all orbiting quite close to their parent star. But because the star is quite small and faint, the middle few planets in that system would be about the same temperature as the Earth. So they could potentially have liquid water and maybe an Earth-like atmosphere. So that's just one example of the sorts of things that we could do with James Webb. What about Ariel? Well, Ariel, because it's got a smaller mirror and because it can't split up the light quite so finely, it's not going to be able to get quite that level of detail, certainly not for a small rocky planet. But because it's a dedicated mission, we're aiming to observe the atmospheres of 1,000 planets. At the moment, we've only been able to do a few tens of planets. And even with James Webb, because we're having to share the time out across all of the different really interesting topics in astronomy, we're not going to be able to do everything we might want to do. So Ariel is going to help us fill in diagrams like this. And I really like this diagram. This was produced by some colleagues of mine. And this is showing what we think might happen in terms of the composition of planets' atmospheres, depending on how big they are. That's the mass on the up and down axis, so how heavy they are, and how hot they are from left to right. So going from left to right, that's colder and hotter. And I've put the solar system planets on there so you can see where they fit. So we think that in sort of the top left of this diagram, quite massive planets and quite cool planets, they're probably going to be mostly hydrogen and helium. And then going more into the middle of the diagram, you get slightly smaller mass planets that might be rocky, like the Earth, like Venus, like Mars, but depending on the temperature, they're going to have different types of atmosphere, maybe nitrogen dominated or maybe carbon dioxide dominated. But really, at the moment, we still don't have a huge amount of information to tell us if this diagram is right. This is based on what we think we understand about how planets behave. Ariel is going to give us the solid facts about this and really help us to refine our understanding of how atmospheres work and what type of atmospheres will arise for a particular planet. So really, James Webb and Ariel, they're a match made in the heavens. And I wrote a little Valentine's poem, since it was Valentine's Day on Monday. Planets are red, or maybe they're blue. Get spectra from James Webb and Ariel too. So it's going to be great having the two of them together, because James Webb is going to provide us with that fine detail, and Ariel is going to provide the wider context and help us understand more about where the planets we observe in detail with James Webb fit in. Because James Webb has that capability for detail as well, we can use James Webb to sort of benchmark our Ariel observations to make sure that we're seeing what we think we're seeing. So together, they're really going to help us hugely advance our understanding of how planets work. And possibly the best thing is, because James Webb's launch was so perfect, it now has enough fuel left for potentially 20 years of operation, which was much, much longer than we originally expected. So that means James Webb and Ariel will be up there at the same time and will be able to overlap. So thank you very much for listening to my science story. I'd love to take your questions now.
Thank you so much. That was really, really interesting. We do have a few questions. The first one being, are you doing what you expected to be doing when you first did that summer placement at the age of 16?
Not exact, sort of yes and sort of no. So I'm looking at planets, which is what I expected to be doing. But I think at the time I thought I'd be doing solar system. At the time, so I was 16 in 2000. So this was the summer of 2003 that I was doing this project. And yes, we knew about other planets around other stars, but at that point, we really hadn't got very far with looking at them in any more detail. And we only knew of a handful. This technique that I'm describing now, it didn't really start being used much until the last sort of 10, 15 years. So this was a field that I just didn't know existed at the time.
No, that's really cool. I think that just shows how much things can change as well in a relatively short space of time, which is really quite exciting. And then tell us a little bit about your experiences when you were young. What really got you inspired into doing science, and in particular astronomy and space science?
So partly my dad is actually an astronomer too. He works on dead stars, not planets, but One of my very earliest memories was visiting his office at the University of Leicester, and they have a Skylark sounding rocket in the foyer. And I remember being really, really small, probably only about 3 or 4, and asking to go and look at the rocket, because I loved going to Dad's work because there was a rocket in Dad's work. And that's quite cool for most kids, I think, if your dad works somewhere where there's a rocket. But I didn't think for a long time I was actually going to go into science, although I always found space quite fascinating, because I didn't particularly enjoy physics at school until the very end of GCSE. I found it quite boring. And the very end of GCSE was a bit more challenging, but I could do it. And I think I realized at that point that I liked the problem solving aspect. So I liked physics when it stopped being about learning to remember formulae and things, and actually started to become about solving problems. And I had an excellent physics teacher for GCSE who really supported me, and basically wouldn't shut up until I agreed to do physics A level. And I really, really enjoyed A level, and really enjoyed my summer placement, and that was really what decided me.
That's fantastic. And it just goes to show the importance of the physics teachers, and of course of your dad as well. Thank you so much for inspiring us into your world, and that's really been very, very interesting today. And thank you for joining us and taking time out of your busy schedule. I know Dr. Barstow also has 2 young girls, and it's half term at the moment, so juggling those sorts of things with online talks as well. I really, really appreciate it. We do have more events coming up at the RAS. They can all be found on our website and also on Eventbrite. Tomorrow we've got the final instalment in these Women Fellows talks. We've got Dr. Olivia Wilkins from NASA Goddard talking about interstellar ice, and my colleague Lucinda Offer will be hosting tomorrow. So until then, thank you again to Joe, and I hope to see you all soon. Take care. Bye.